This is a high-speed recap of Level 2 magnetism. Don't forget to use your pause button. I'll work my way through all 17 pages of your handout bundle, and there are a couple of pages that I skipped because hopefully they're self-explanatory or described in the text. So here goes. Some reminders. If we pass a current into a conductor, then that conductor will produce a magnetic field which flows around it. So flux flows around that conductor. If we talk about the current going in, this is how we represent current going in, and the flux around that conductor is going to be in clockwise direction. If we were looking on the other end of it, then the current is coming out, and oops, not very well drawn, and the flux flows anti-clockwise. Moving on, if we have two conductors which are next to each other and they have the current going in the same direction, then now what happens is this is going clockwise, this is going clockwise, and at this point they tend to merge and we get something that looks like that. So this will result in a force of attraction where this and this are pulled together. If we move on to opposing currents, so we have one going in, one coming out, and we draw this hopefully tidier than mine. This is clockwise, this is anti-clockwise. Then at this point the two fields push together, and as a net result these conductors will have a force on them that will push them apart. This is a force that they are pushed together. Moving swiftly on. So here is a former. If we have a coil of wire, like so, and we pass a current into the coil of wire, we produce an electromagnet. This electromagnet will have a north pole and a south pole. We can check that with the right hand grip rule. If we follow this wire that goes up over the top with your fingers, wrap your fingers around the magnet and your thumb points north. So this is north, this is south. We can change the strength of this magnet by doing one of three things. Number one, we can increase the number of turns. More turns, stronger magnet. Number two, we could increase the current. Increasing the current, a stronger current will produce a greater magnet. And the final one is insert an iron core into there. So if we make this an iron central piece, a core or a former, then that will focus the magnetic field on the poles and it becomes much stronger. Moving swiftly on. So here I've drawn quite simply a traditional permanent bar magnet, and the magnetic field will be from north to south. North to south. So the flux flows north to south. This is a fixed permanent magnet. This is a coil or an electromagnet. And here the electromagnet that is produced in a straight bar like this will produce an almost identical magnetic field. So with a current flowing in there, this will produce a flux which flows north to south. Hopefully you can see the similarities. So developing that a little bit further into the electric motor principle, if we place a loop of wire, a conductor, in between the faces of this magnet, like so, and we then pass a current into this loop of wire, we'll produce the beginnings of an electric motor. So what is happening is the current on this side is influenced by the magnetic flux travelling north to south, and then the current on the other side is actually travelling in the opposite direction on this loop, and that will be influenced. And we can draw that down at the bottom down here. So here is our loop. There's the loop of conductor, current going in here, current coming out there. From north to south, if we think about the flux around this and the flux around this, the flux wants the easiest path that it can find, and it's going to go over the top here and under the bottom there. So it goes in the same direction there and the same direction there. This turning of the flux results in a force that pushes this conductor down, and this conductor goes up. So back to the loop, this side will go down and this side will go up. So we have the beginnings of rotation. Okay. So the next page on your handout bundle is about the force produced by a current carrying conductor in a magnetic field. I'm going to skip that. Hopefully that's self-explanatory. There's an example on there. The next step takes us to generating electricity. So we've just looked at a motor. We're now going to look at generation. For generation you need three things: coil, magnet, and movement. As long as you have those three things, coil, magnet and movement, you have the ability to generate electricity. So in this particular scenario, we've got the fixed magnetic field north to south, and we have a single loop conductor placed within it. The difference now to the motor, with the motor we pass current into the loop and it turns. In a generator, we have to put physical energy, mechanical energy into the loop to turn it, and it will then produce electricity as the loop passes through and cuts through the flux from the main field north to south. So we would take the electricity off using slip rings. You notice I haven't drawn them because it's a bit too technical and take me too long to do it. It's on your handout and it's hopefully a lot clearer on there. So we take the electricity off using slip rings. We'll see this later on when we look at motors in more depth. So the next couple of pages, so 5 and 6, will show you the stages of rotation of this loop and how we generate the sine wave. So if you rotate a single loop coil within a magnetic field, it produces a sine wave. So I'll attempt to do it high speed. It'll do. So there is the peak. And we have a couple of notable values. The most common one that we use is RMS. So Rms Voltage, VRMS. And that is 0.7071 times the maximum or peak. And another common value that we use is average, V AV, so RMS is there, 0.7 of the way up, and the average is 0.637 times the maximum value. If you were to put some numbers into this and you wanted to find the peak value, then the peak value, if it is 325, if you do 0.7071 times 325, you will get 230, which is our typical nominal UK supply voltage. On to transformers. I'm skipping through several of the pages here. This is page 9, and there's an introduction given to you there. I'll just label this up. We have the incoming supply voltage, so this is the primary voltage. This will pass a current, the primary current, and we have a number of turns on the primary, NP. On the secondary side, if we label it up going in the same order, or reverse order I should say, there's the secondary turns, the secondary current goes out to feed your circuit, and this is your outgoing voltage, the secondary voltage. Key phrase at this point is mutual inductance. Mutual inductance. If we pass a current into this, then the primary produces a magnetic flux which expands outwards. The lines of magnetic flux cut the secondary winding and induce an electrical voltage, an EMF, in the secondary, and we can measure that there. So what we have is two totally separate electrical coils, and the primary produces electricity in the secondary without touching it. They are working together, and in this instance this is what mutual means. They work together. The flux from the primary cuts into the secondary, and we pass voltage from the primary to the secondary. We pass current from the primary to the secondary. So mutual inductance, and it means working together. Okay, next couple of pages. So page 11 goes into different core constructions. Page 12 goes into different styles of transformer arrangement, and that takes us to page 13. So page 13, we have this diagram again, and it discusses the labelling. This labelling on page 13 is important: VP, NP, IP, VS, NS, IS. So if you label up that diagram, there is a box down at the bottom that summarises the formulae that apply to transformers. So VP over VS, NP over NS, and the current swaps IS over IP. So voltage and turns look the same: primary on top, secondary on bottom. The current swaps: secondary on top, primary on bottom. And if we move quickly on to page 14, I'll pick up a very simple example. Ooh, not very well drawn, but it'll do. So let's suppose I have a transformer that has 2000 turns on the primary, and it has 200 turns on the secondary. Then this has a ratio of 10 to 1. So the primary turns are 10 times greater than the secondary. What that means to us is if we stick with this ratio, if we put 230 volts in as our primary voltage, then this ratio applies, and we will get an output voltage of 23 volts. It's 10 times less, 10 to 1. The opposite happens with current in a transformer. So for example, if the current at this point, the primary current, is 2 amps, then this ratio works in the opposite, and it would be delivering 20 amps on the secondary. That's an important point to note, and that is page 14 of your handout bundle. just take it a bit further. So page 15 is further transformer calculations, things you're expected to know at this stage. Quick sketch of a transformer, that'll do. And if we look at example 1, a transformer has a primary current of 2 amps, a secondary current of 6 amps. Find the number of turns on the primary if it's got 500 turns on the secondary. So there's 500 turns there. What is the primary turns? Okay, so the formula is going to involve current and turns. So you can only use 2 of them at a time. So MP over NS is IS over IP. The primary turns is what we want to find. Do a quick transposition, that will move to the top. So primary turns is IS times NS over primary IP. Put the numbers in. 6 times 500 over 2 is 1500 turns. Hope that made sense. If you go to page 16, there are a few more questions if you want to do them. There's no great push on that at this stage. Final page, page 17. So page 17 is looking at transformer KVA rating. I've got another sheet, no, on my last sheet of paper. So the KVA rating of a transformer is taken from the secondary winding, and its ability to deliver its maximum voltage and maximum current will give you the KVA rating. So let's do a very simple calculation. If this is 12 volts and this is delivering 2 amps, then the volt ampere rating is literally the voltage times the current, nothing more. V times I. If you put the numbers in, the voltage is 12, the current is 2, that gives you 24 volt amperes. So that's nice and simple. Let's do a different example, and I'll try and squeeze it in. So on this example, let's say we've got a 230 volt output voltage and it's delivering 13 amps. So 230 volts, 13 amps. What is the KVA rating of this transformer? KVA is voltage times current. Put the numbers in. 230 times 13. I don't know the exact number, it's a fraction under 3000, but I'll call it 3000 volt amperes. So it's 3000 volt amperes, or alternatively it's 3 kVA. Okay. Watch the video through again, do it step by step, pause whenever you need, and fill in the gaps on your handout. Good luck.